Elsewhere, we talked about this estimate for the divisor counting function, sum n less than x of the number of divisors of n was x log x, and then you had a lower order term 2 gamma minus 1 times x, and then you had some error term that was power of x. And here gamma is the Euler-Mascheroni constant, 0.577, etc. There's also this identity that the Dirichlet series, sum n from 1 to infinity of the square of the divisor counting function over n to the s, is equal to the fourth power of the Riemann zeta function divided by the Riemann zeta function at 2s. And reference for this is Hardy and Wright. This is theorem 304 in that book. And it's just some Euler product thing. And of course, this gives you this asymptotic estimate, sum n less than x of the square of the sum of divisors function is equal to x times, and here I'm just going to write some polynomial of, it's going to be degree 3 in log x, and then you're going to have some error term that's some smaller power of x. So this is and in general, when you want to study the distribution of some quantity, say the number of divisors of an integer n, one way you can do that is you can look at moments. And that leads naturally to the question of asking about the sum n less than x of the rth power of the divisor counting function. Now, actually doing this is going to end up being too much work, so instead I'm just going to direct you to a reference, tell you where you can find it. So references I'll give are Wilson 1922, which elsewhere I may have said 1923, sorry. And there he proves that the sum n from 1 to infinity, so the Dirichlet series of the divisor counting function to the rth power over n to the s is equal to the zeta function to the power 2 to the r, and then here he has some function phi of s, which is, I think he says it is holomorphic for this sigma is the real part of s. Sorry about that. Strictly greater than 1/2. So he basically says it's the 2 to the rth power of the Riemann zeta function. And from this, maybe a nicer reference for this is this paper from Florian Luca and Laszlo Toth. From 2017, where they just restate Wilson but in a way that I find a little bit clearer, that sum n less than x of the rth power of the divisor counting function is equal to x times, and then here there's a polynomial of of degree 2 to the r minus 1 in log x, and then the error term is x to the 2 to the r minus 1 over 2 to the r plus 2 plus epsilon. And the leading coefficient of this degree 2 to the r minus 1 polynomial is given by 1 over 2 to the r minus 1 factorial times a product over primes of 1 minus 1 over p to the 2 to the r. This is going to be coming from the Riemann zeta function essentially. And then there is the sum alpha greater than or equal to 0 of alpha plus 1 to the r over p to the alpha. So they give you some explicit expression for the rth moments of the divisor counting function, at least asymptotically. It turns out that these are not that useful for actually reconstructing the distribution in practice, because going from moments to actual distributions tends to really magnify your error terms. So my guess, without having done it myself, is that probably you're not actually going to get reasonable error terms this way, but it still tells you a lot about the distribution, and it can also let you guess what the distribution should be. So this stuff is kind of cool, and it's just sort of the natural extension of the questions that we've been asking so far about the divisor counting function.